Well, good morning, everybody. We'll go ahead and get started. Thank you for joining today. My name is Heather Hoffman. I'm the federal liaison between the WestFAST and the Western States Water Council and host of today's presentation. Please do note this webinar will be recorded and posted to the WestFAST tab found on the Western States Water Council webpage at westernstateswater.org. So feel free to share that link with those who you know could not participate today. Today we're going to hear about water supply forecasting from Dr. Sean Fleming, who is the Applied R&D Technical Lead with the USDA Nrcs National Water and Climate Center and holds positions at Oregon State University and University of British Columbia, Vancouver. Dr. Fleming's experience includes a couple decades in public, private, academic, and nonprofit sectors, spanning technical, field, and managerial roles. He has been involved in operational river prediction since 2007 and hydrologic applications of artificial intelligence since 2003. Before joining NRCS in 2019, Sean ran a data science consultancy for several years, and prior to that led an applied R&D unit with the Meteorological Services of Canada. He holds degrees in geophysics, geology, and civil engineering, and his work focuses on bridging gaps between theory and practice. He is also actively engaged in public engagement around science. Examples include publishing a general audience book with Princeton University Press and essays in Scientific American and Wired, as well as giving public talks at the Smithsonian and elsewhere. So before I hand it over to Sean, I want to let you know that we will take questions at the end of today's presentation. You'll also be able to use the chat feature, or at the end, simply unmute yourself to speak. If, as we go along, you have questions, please capture them using the chat, and I'll be happy to read them aloud at the end of the presentations. So please use the chat feature during the presentation and I will read them at the end, or when we're finished, unmute yourself to speak. With that, that's all the housekeeping, and I will pass it over to Sean. Take it away, Sean.
Great, thanks, Heather. I'll start by sharing my screen here. Whoops, that was the wrong one. Bear with me here. I can navigate AI, but basic IT is beyond me, apparently. Let's see here. Okay. Can you see my screen, the presentation, Heather?
Yes, I can see it.
Awesome. Perfect. All right. Well, thank you very much for the introduction. Yeah, so today I'm going to be speaking about what we're calling M4, and it's the next generation of the NRCS water supply forecasting system for the U.S. West. And it's a little distinctive in that it is based on machine learning. So I'm going to start off with some punchlines. So this is one of the oldest and largest operational hydrologic prediction systems in the American West. The resulting meta system is, it represents, as far as we know, the largest transition of machine learning into a genuine operational hydrologic prediction setting so far. So we're kind of excited about that. That was a bit of a hurdle in a sense, maybe as much psychologically as technically within the water resources community. And it was made possible by understanding the needs of the operational water resource science and engineering community and working hand in hand to build the right kinds of solutions, things that'll work. And this in turn opens some doors to more sophisticated forecast product integration, as well as a whole bunch of other things going forward, or at least that's our hope. And there's good reason to believe that this will enable some kind of spin-off directions going forward, but we'll get to that later. So let's start off with a little bit of background, just so we're all on the same page. So in the water resource science and engineering and management community in the West, Operational water supply forecasting has a pretty specific meaning. So these are forecasts, and they're typically issued once a month at the start of the month, but also more frequently depending on the agency and the location and things like that. And this forecast process begins in winter. And the forecasts are of the upcoming spring-summer flow volume for a given point on a given river. And that's done on a river-by-river basis or a forecast point by forecast point basis. And when we mean operational, when we say operational, what we mean is that it's being performed by institutions like NRCS, the river forecast centers of the National Weather Service are another example. There are a few others who have direct accountabilities to end users around the reliable generation of forecast products. And these forecasts provide the practical basis for water resource management in the US West and in Western Canada as well. And these models typically emphasize snowmelt contributions to flow. So it depends exactly on how you phrase it, but anywhere between 50% and 90%, most estimates are around 70 to 80, depending on, again, where you look, of the spring-summer runoff in rivers in the US West are derived from mountain snowmelt. So the mountain snowpack is essentially this gigantic de facto reservoir, high mountain reservoir from which the spring-summer runoff is derived, which in turn is the time of year when it's needed most. So that's kind of handy. And it's also the basis of the modeling, the forecast models used to predict that flow, specifically measurements of mountain snowpack, that is. Other predictors include, measurements of precipitation, antecedent stream flow, which captures things like soil moisture and groundwater, contributions to flow, climate indices, a few other things. And the value of these forecasts is pretty amazing. It's interesting, there's been a lot of work on valuing water in the environmental economics literature, but no one really, as far as I know, has a great number for just exactly how much water in the West is actually worth. And there are some back of the envelope estimates as well of the value of water supply forecasts and also water supply forecast model improvements, but not a lot. But the numbers that or the studies that are available, and there's just one or two, do suggest that even incremental improvements in a water supply forecast model can be easily worth well over $100 million a year in public benefit just for one basin. So these things are important, and improving them is also important. So a little bit of context about the NRCS. The USDA snow measurement and water supply forecasting processes found their origins in the Dust Bowl of the 1930s, and we've just been continuing to do that ever since. We operate the Snowtail Network, for instance. The National Water and Climate Center, which is where Heather and I work, of the NRCS in Portland, currently operates the largest standalone operational water supply forecast system in the US West. I think if you took all the National Weather Service river forecast centers and combined them all together, it might be a little bigger. I'm not sure, but it's big is the point. And it may be the largest statistically based WSF modeling system globally. So there's over 600 forecast locations. So this thing is pretty big, spans the Western US and Alaska. Each of those locations has multiple issue dates, typically starting in January and February through March, April, May, June in some cases, as well as target periods. So that's kind of the forecast horizon. There's several different models and currently in use at NRCS, but the core method is principal component regression, or PCR. This is a variant of linear regression that has some nice technical advantages that are useful in specifically in a water supply forecast context. And it was introduced to water supply forecasting by my predecessor in National Water and Climate Center, David Guerin, in the early 90s. And it's proven very successful. It's been adopted by a number of other organizations in Western North America. It's worked quite well. That said, it's a couple decades old. There are some known technical issues with it that we'd like to address, and we're also curious to see, if the other emerging data science technologies out there can provide some, tangible advantages over these existing, proven but now rather old statistical methods. So that's what we embarked on. Before jumping into the model, there's a bunch of context to designing these systems that's important and kind of sets it apart a little bit from what you might, I suppose, call more purely academic work. Because this is an operational water supply forecast system, and there's a bunch of additional constraints that are kind of around it. So we started off with some preparatory steps. Clearly documenting the existing system was a good starting point. It's reasonably well documented, but again, it was implemented about 25 years ago. And these systems, if you're familiar with them, whether it's at NRCS or elsewhere, they're complex and they're kind of organic. They evolve over time as you gain experience and more data types are available and community needs change. Then, of course, moved on to assessing the capabilities and limitations of that existing system. So that's documentation of known issues, but also we did a bunch of advanced statistical diagnostics on the existing system. A pretty comprehensive review of the data-driven water supply forecast modeling progress out there, and an assessment of its potential relevance to NRCS operations. We also assessed the implications of global climate change and water supply forecasting. So that's kind of an interesting one because this is a seasonal scale forecast problem. We're not looking forward 20, 30, 40, 50 years. It's not a climate change impact assessment modeling exercise. We're looking forward just a few months with each forecast. But climate change does have some implications for water supply forecasting. And in terms of both the kind of day-to-day operational protocols, and in particular, emphasizing the need to improve the accuracy of our models. One of the impacts of climate change is to essentially decrease the skill of water supply forecast models. And this is because it's primarily a temperature effect. As it gets warmer in winter, more of your precipitation falls as rain instead of snow, especially in the shoulder seasons. So the snowpack is decreasing. And that because water supply forecast models, the fact that we're able to actually make these projections months ahead, in spite of the fact that weather models are only good for like a couple of weeks, that is all due to the fact that we have these great measurements of mountain snowpack and that the runoff is derived from mountain snowpack. So if that snowpack is starting to decrease, that has all sorts of trickle-down effects to water supply forecasting and really emphasizes the need to find additional or alternative sources of prediction skill in our next generation models. Of course, that also has broader implications in terms of water supply and demand, also when you combine it with population and economic growth in the West. So moving on from that, we also developed some initial blueprints and did a bunch of preliminary scoping work. So what we landed on is machine learning as the solution that we wanted to go with. And really the punchline there is just that it has overwhelmingly good bang for the buck as a predictive tool. There are advantages and disadvantages to it, but it just clearly a great direction going forward, especially if you're committed to primarily a data-driven system. That said, a lesson that's been learned in certainly hydrology, but many other fields as well. I've worked with some material science applications, for example, and they run into exactly the same issues, is that you can't just take these off-the-shelf machine learning technologies, just grab one and then just throw it at hydrologic prediction and expect it to work well. You have to approach it in a very application-specific way and choose the right tool for the job, or if it doesn't exist, build one of your own that suits those criteria. So let's dive a little bit deeper into the history of machine learning and hydrologic prediction. This is not a new field. The first research papers that I'm aware of using AI for river forecasting date all the way back to 1995. Yet, in spite of that true operational adoption of machine learning in a genuine operational forecasting context is mostly very, very recent and very, very limited. There's a caveat to that. A lot of operational organizations don't, it's just not necessarily in their mandate to be publishing papers and things like that. So, and in some cases, with hydroelectric utilities, for example, in certain cases, it's actually in their competitive best interest not to let the whole world know exactly what they're doing in terms of what technologies they're using and trying to gain that predictive skill, which is in turn important for things like futures trading and of electricity contracts and things like that. I'm actually aware of a hydroelectric utility that was using ANNs operationally for forebay elevation forecasting back, I don't know, 2001, 2002, something like that. But you would never know unless you actually talk to their engineers because nothing was ever published on it. But the bigger picture is that AI has not seen very much adoption in river prediction, whether it's flood forecasting, water supply forecasting, or anything else in an operational setting, in spite of having been demonstrated to provide good accuracy. So why is that? And there's a few reasons. Kind of broadly, I built my own neural network in like Fortran on a SunSpark workstation, I think, back in close to 20 years ago. I've been sort of tracking this remain involved on and off ever since with AI applications to hydrology. And it's really been interesting watching how the community, the sort of attitudes of it, how those attitudes have changed and also how they haven't. There's definitely been a bit of a bah humbug attitude about machine learning in hydrologic circles to a significant degree. And that's not without some justification, though it's also been a hindrance in some ways. There are some more quite specific issues. One is the black box nature of machine learning that just doesn't sit well with a lot of physical scientists and engineers. Lack of uncertainty estimation, quantitative uncertainty estimation around the best estimate is another issue. There are several, fairly specific technical things. So, of course, it's really amazing how quickly that has all changed in just the last 5 to 10 years. Everyone is just getting used to the idea of AI. So people are just becoming more comfortable with using these technologies. There's a lot more tools. They're a lot more accessible. The methods are a lot more diversified. And things like explainability, prediction uncertainty estimation, these things can be addressed if we do it carefully. But again, we can't just take these methods and just throw them at hydrologic prediction problems and expect them to work well. So ultimately, it comes down to this Venn diagram. So what you need is this convergence, this intersection between a balanced and mature understanding of the machine learning methods that are available, how that intersects with the detailed body of hydrologic and climatic process knowledge, and then in turn how that intersects with just the day-to-day needs of a genuine operational forecasting environment. So out of all that came a number of specific design criteria. So this was like, okay, never mind what techniques you're going to use. This is what the system needs to do. All right. So I'll just run through these fairly quickly. Improved forecast accuracy is obviously something you want. Improved potential for automation was also a significant issue. So to use the terminology from the operational forecasting community, what we're looking for here is a largely, though not entirely, over-the-loop system. There's a whole bunch of pragmatic issues in an operational environment, reasonable cost, ease of deployment and operation, things of that nature. There are also some specific known technical issues with the existing system that we wanted to fix. So these are things like nonlinearity, some statistical complexities around the prediction uncertainty intervals that conventional linear Gaussian statistical models just don't handle well. Looking forward, modularity and expandability of the architecture of whatever it is that you build is really important to be able to capitalize on newer methods as they emerge, and to avoid obsolescence. Something that's particularly important, especially when you're looking at AI solutions, is this notion of physics awareness. So this is a combination of having machine learning methods that are guided by hydrologic theory, and are also, the model predictions at least are readily explainable in terms of known hydrologic and climatological process knowledge, to form those storylines that are really important for understanding and communicating the water supply forecasts. That's critical. There's other practical things like, balancing, innovation and the performance gains that you want to, get with the next generation system versus also, using established building blocks and proven tools. I'm not going to dive too deeply into the background around this, but having a multi-model ensemble is really important. This deals with issues of model selection, uncertainty, and equifinality, which are really, really important known issues with hydrologic modeling and modeling in other fields as well. And the ability to accommodate high dimensional predictor data sets. So, large data sets that have some multicollinearity in them. Again, that's the kind of thing that's only going to grow more important in the future with more spatially distributed inputs like satellite remote sensing, global climate models, or seasonal to subseasonal climate models, things like that. So that's all the background to it, more or less. And the solution we came up with, we're calling the multi-method machine learning meta system, or M4. And I'm not going to go into the technical details of it in any great degree here. I'm just going to kind of sketch the outline of it, and I'd be happy to answer more detailed technical questions later. The basic premise is more or less captured by this simplified flow chart. So you define the hydrologist, the operational hydrologist, when when applying this to a particular river, defines a pool of candidate input data variables just as they would with a conventional statistical model. Then principal components analysis, which is a form of unsupervised statistical learning, is used to extract patterns from that data. And then these in turn form the predictors, or to use the machine learning nomenclature, the features that are fed to each of 6 different statistical and machine learning prediction models. So this includes a couple different kinds of artificial neural networks, random forests, support vector machine, quantile regression, a few different things. And this is why we're referring it to a meta system, because it's actually a collection of 6 semi-independent water supply forecast systems. Then a global stochastic optimization algorithm, specifically a genetic algorithm, so that's a kind of evolutionary computing, is used for feature optimization. So what that amounts to is selecting the best performing combination of input variables from that pool of candidates, as well as corresponding principal components analysis modes to keep in the final model. When that's done, each of these models generates a best estimate with prediction intervals. And then, or in other words, a forecast distribution, a probability density function. And then each of those forecast distributions, they're all lumped together, they're all averaged together to generate a multi-model ensemble mean forecast distribution. There's a little bit of QC diagnostics and model pruning done after that to kind of fine tune it a little bit, and then you're done. So the final product is a best estimate with prediction intervals generated by these various different systems. Again, it's integrated, it's modular, it's expandable, and all the different components of it were selected in specific ways that met those, I believe it was 9 design criteria that we went over in a previous slide. And each of those methods is also, although the combination, the resulting meta system is kind of a novel hybrid technology. It's built from parts that are all individually well proven and just known to work well. So again, I'm not going to go too deeply into that, but I would like to emphasize two aspects of it that I think are particularly relevant to an operational forecasting environment. One is kind of getting back to that question of the black box. This is the big, criticism of machine learning. It's something that's really being overcome in a lot of ways, but there's still a lot of work to do on that. Some current directions in machine learning, ironically, almost feel like they're kind of going in the opposite direction. You'll note that there is no deep learning in the system, and that's one of the main reasons why. There's a few others as well. Not to disparage deep learning, is very useful for certain purposes, but again, it's about the right tool for the job. And at the moment, given current technologies, deep learning is not the right tool for the job. So that said, how did we achieve that intersection between machine learning and your understanding of process physics and the ability to tell a storyline about the forecast when you're done? So there's a bunch of pretty pragmatic steps that we took to help ensure that. One is to maintain the role of the operational hydrologist in using their subject matter expertise in the features engineering step. That's largely about picking what predictors you use. And that's really where, like a great place to insert your physical hydrologic knowledge into the process. And so this is not a data mining exercise. It's quite different. There's a lot of hands-on ability given to the hydrologist to insert that knowledge in there. Another key step was to reframe the entire thing as a low-dimensional problem with a parsimonious solution. So that's just a fancy way of saying that we can take a lot of complex things, a lot of different input data sets, and collapse them into something much more compact. And then together with trying to find the most parsimonious architectures for the machine learning, what you wind up with is the ability to actually graphically visualize the relationships between the inputs and the outputs, the predictors and the water supply forecast. And that lets you understand in a pretty direct way what it is that the machine learning algorithm is thinking, so to speak, when it's coming up with these predictions. There's a few technical aspects around the particular methods that we adopted and some QC algorithms that we developed into M4 that also allow us to enforce some a priori physical knowledge on the solutions. The other aspect that I'll emphasize is autonomous or automated machine learning. The jargon for that in the AI community is AutoML. To my knowledge, this has not seen any prior application in hydrology. We've kind of done a baby version of it here, but it meets our needs. So we don't actually want completely hands-off operation. Something that operational hydrologists want is the ability to get in there and modify things and tinker and insert their expert knowledge. But that said, if you're going to build a machine learning system, a fairly complicated one, and then expect the operational hydrology community to actually use it, this is a community whose expertise lies in something other than AI. You're going to have to streamline a lot of the sort of detail tasks in the machine learning part of it. Plus just the scale of the problems that you're dealing with. You've got over 600 forecast points. You need to kind of streamline things and have some automated logic in there. So this kind of again, as I mentioned at the very, very start, this ties in with meteorological and hydrologic community concepts around over-the-loop systems. So that idea of AutoML kind of dovetails quite nicely with that. So what that means in practice is that there's a whole bunch of optimization and decision points in M4, and they're all either automated or they've been kind of pre-calibrated to reasonable default values on the basis of some very extensive testing that we've done. That said, there are options for manual overrides, which again is very important for the operational hydrology community. So that's the system. How does it work? How well does it work? Let's start off with just a specific example. This is the Owyhee River near Rome, headwaters in Nevada and Idaho. The forecast point itself is in southeastern Oregon. So we're going to look at the April 1 forecast of the upcoming April-July flow volumes. Now, this is a particularly troublesome forecast point in a number of respects, and we'll see why in the next slide. So it's a pretty challenging example for any forecast system. So this is kind of our benchmark. This is what the conventional linear existing PCR solution. This is the operational method in use at our NRCS and a number of other organizations. This is what PCR does with the problem. And you can see right off the bat, there are a few issues, right? So what you're looking at here, take a step back, sorry about that. The red dots connected by a thick red line, those are the observations. So this is kind of a hindcast exercise here. So we're looking from 86 to 2015. The red dots are the April-July flow volume observed in each of those years. The black line is what the conventional water supply forecast system predicts, and the gray lines around that best estimate prediction are the prediction intervals, the confidence intervals. The flat red line at 0 is simply a reference point for zero flow. And so I mentioned right off the bat, you can see some problems here. One is that it's making a bunch of negative flow predictions. So negative river runoff volume can't be negative. It doesn't mean that the river's flowing uphill or something. It just means it's just wrong. And there's also some issues with the prediction intervals. They're not really capturing the points quite correctly, and there are a number of issues there that I won't go into too much depth right now. Basically, there are problems with it. And some of this is fixable in traditional linear Gaussian statistical modeling using things like predict-and transforms. But there's a lot of problems with that process. It's manual, it's subjective, it's slow, it's got reproducibility issues. So you can kind of jury-rig it to work better than what I'm showing here, but it's just not a great solution. In contrast, this is what our M4 system does. There's been no manipulation here, nothing. We just fed it a bunch of the same input variables we fed to PCR, hit the go button, and this is what it does with it. Excuse me. So all the predictions are physically reasonable. The prediction bounds around that best estimate are reasonable. There are a few other benefits to it. Excuse me. Sorry about that. It's relatively robust to outliers, and the whole thing is automated. There's no user intervention. There's no subjective criteria going into, or subjective input going into developing this prediction. Yet it's still relatively simple to cheap to build and operate. So that's just kind of just an anecdotal example in a way. The more rigorous testing consisted of some hindcast testing and some operational forecasting. Next two slides will be about that. So let's start off with the hindcast testing. We picked 20 test cases corresponding to 11 basins all across the western U.S. and Alaska. So they were picked to sample really diverse geophysical environments. I mean, all the way from glacier-fed rivers in Alaska to a desert basin in southwestern New Mexico, as well as a variety of statistical characteristics known from the diagnostics we did and also just operational experience at NRCS. We also used the existing NRCS PCR system as a benchmark. It's actually a fairly challenging benchmark. It's a well-established method. It's known to perform reasonably well as far as these things go. And various other studies have demonstrated that its performance is about on par with the process simulation model-based ensemble streamflow prediction or extended streamflow prediction, ESPs, that are used by, for example, the National Weather Service River Forecast Centers and other groups. So it's a meaningful benchmark, a broadly meaningful benchmark. And the punchline is that M4 meets or almost always beats that conventional benchmark on both deterministic and probabilistic performance metrics. So some of these are pretty dramatic. On average across these 20 test cases, we're looking at improvements of about 55% in R-squared values, a 13% reduction in RMSE, a significant improvement in the rank probability or RPSS, which is a measure of how good those prediction intervals are. as well as physicality. It's also the ensemble mean that comes out of this meta system consisting of 6 independent AI or statistically based prediction systems is more consistent and typically sometimes actually outperforms any of those constituent 6 models. And that's to be expected. That's just part of how multi-model ensembles work. So we were hoping for that and we saw it, so that's great. And then again, after candidate predictor selection, that pool of potential input variables that you want the algorithm to consider. After that, the entire thing was just completely hands-off, completely over the loop system. So in terms of operational testing, we did, this is kind of the harder test in a way, to confirm the logistical feasibility of the workflows in a time and data constrained, genuine operational setting. We did this at a subset of 5 forecast locations, which are, selected to be very diverse during the 2020 forecast season. And we ran alongside the existing operational system, of course. So everything worked, which is nice to see for a first live operational testing of a prototype. As a bit of an anecdote here, some of the models, just because of data availability constraints from snow survey sites, due to COVID-19 quarantines, there just weren't some data available. So we were able to rebuild some of the models on the fly without, omitting those particular locations that were reliant on manual snow surveys rather than SNOWTEL or other automated and telemetry sites. Part of the reason we were actually able to do that, because some of these machine learning methods, they take a lot of time to train a model. And, again, this comes back to some of the design choices that we made in M4, as well as the use of a limited level of parallel computing. We're not using any high performance computing resources here. This is just running on PCs, but we're able to distribute some of the tasks across cores on the machine, and that really sped things up as well. The test was really to make sure that the thing would actually kind of physically work and be feasible in a genuine operational environment. On the basis of 5 forecasts, well, it doesn't matter how many locations there are. If you're just looking at 1 year, that's really just one sample in a sense, and it doesn't give you a great quantitative estimate of how much of a prediction forecast I'm sorry. I'm losing my voice a little bit here. Doesn't give you a great impression of how large the accuracy improvements will be in your forecasting. That's what the hindcast testing that we just talked about is all about. But still, you'd hope that it wouldn't tank. and it didn't. It actually improve the forecast skill in some cases quite substantially across these basins and this is starting in January, so we're doing multiple forecast cases: January, February, March, April, so it did improve the forecast skill relative to the existing system, which is nice to see, and expected on the basis of the hindcast testing. Another interesting aspect to it, and this was actually a little bit surprising in a sense, is that the stability from one forecast date to the next was improved. So what we're talking about here is we're predicting, for example, April, July flow volume, and you do a January forecast of that and a February forecast of that and so forth. How much does that forecast jump around from one of those forecast dates to the next? And there is very little effort made in this system to really enforce predictor consistency from one forecast date to the next, which is a very common practice in existing operational forecast systems. So one concern might be in that case is that you're going to get a bunch of fluctuation from forecast date to forecast date on what that final flow volume is going to be. In fact, it turns out that M4 actually had less variability from one forecast date to the next than the existing system. So that's actually really nice to see. And then finally, and I'm not going to have time to get into this here, but if you kind of just do a little bit of digging into the products that M4 generates, it's actually really easy to produce a straightforward physical storyline for the issued forecast. in terms of the current conditions, what's the SWE in the basin, has it been a dry year, wet year, stuff like that, as well as known hydrologic processes. And it can do things like identifying known forms of nonlinearity that kind of tie into the climate elasticity of precipitation, various different things like that. They're all well known in the hydrologic community. So everything just seemed to work pretty well. So I'm going to just wrap it up here. In terms of current and next steps, the big step from taking M4 and putting into really a full production environment across the entire forecast system, all 600 plus forecast points, is to build a nice interface for it to sit on. Right now, it's just a raw R script with thousands and thousands and thousands of lines of code. It's a little clunky to just in terms of importing data and things like that. So there's, any operational forecast system has all sorts of database linkages. It needs a nice graphical user interface, all sorts of things like that. So we're in the process of building a prototype or doing some R&D around building that platform. There's a bunch of other applied R&D directions. We're collaborating with Los Alamos National Laboratory on supplementing that initial feature extraction step with another alternative, a brand new machine learning technique called non-negative matrix factorization with k-means clustering. Quite a mouthful, so NMFK for short. A bunch of different WSF predictors. So there's a ton of these out of the remote sensing literature, out of the seasonal to subseasonal climate forecasting community, all sorts of different things that are out there, and a flexible nonlinear AI that can handle high dimensional data, which is what our system was specifically built to do, should in principle be able to capitalize on those kinds of predictor data sets more effectively than traditional technologies. And then again, this is a meta system with several semi-independent systems. It's a multi-model ensemble platform. And that in turn enables a bunch of other things. So certainly we can integrate other AIs into it, but another interesting idea is the notion of ingesting forecasts from external sources. So that includes things like process simulation models that we run internally. WRF hydros is being looked at for seasonal water supply forecasting, and of course there is the National Weather Service River Forecast Center ESPs that could be ingested into this and include as just another model in that final ensemble. So this is kind of a de facto opportunity for reestablishing interagency forecast coordination that used to exist but has largely ceased over the last few years. So I'll wrap it up there. If you're interested in learning more about what's under the hood of this thing, the algorithm itself was published in the peer-reviewed machine learning literature. So here's the reference as an IEEE paper. It's open access, so you can just Google it and access it. Or of course, you can contact us. I'd be happy to send you a copy. There's a few additional papers in progress around other aspects of it. So with that, I think I'll hand it back to you, Heather. Thank you.
Thank you, Sean. So we're now going to open it up to questions. You can unmute yourself and ask Sean your question directly, or use the chat feature and I'll read your question aloud. There's one question in the chat now. I'll start off with that one. So the question, Sean, is the hindcast forecast time April 1st?
The hindcasts were done for two forecast dates. January 1st is an early season forecast, and April 1st is kind of a mid to late season forecast.
Okay, great, thanks. All right, anyone have a question for Sean? Oh, here's another one coming through the chat. Did you test the assumption that the manual predictor selection by hydrologists improves forecast skill?
Well, the question is, what is the alternative? There is no real alternative to manual predictor selection in the sense of the pool that we generate. So actually, this will, is my screen still being shared? Can
yes.
you? All right, awesome. So when I say manual predictor selection, what I mean is the definition of a pool of candidates. And then what happens is this genetic algorithm works alongside the PCA-based feature extraction and each of these semi-independent statistical and machine learning models to pick the optimal predictors for each of those models. So in any given case, that whole pool of variables, in almost no case are all of those actually retained in the final models. It picks the ones that works best. And this is a little like existing systems. Principal components regression has a relatively simple tree algorithm for picking the optimal input variables. And this is just kind of like a significant step up from that, but it's the same concept. So in this, in M4, there are algorithms for optimizing that. The hydrologist still does need to provide it with input data on the basis of his or her expert judgment. And that's something you're not really going to get rid of, and you probably wouldn't want to anyway. Because I mean, what is the alternative? Are you just going to feed it, the internet? You have to, you have to tell it, you have to provide it with some kind of data, and then the algorithm itself makes optimal choices about which of those candidates to keep.
Great, thank you. All right, here comes in another question. Is there a way to apply M4 to determine where improvements in the accuracy of data sources for input variables would have the greatest benefit for model training and forecast accuracy?
Can you repeat that question? I didn't catch the very first part of it.
Yeah, is there a way to apply M4 to determine where improvements in the accuracy of data sources for input variables would have the greatest benefit for model training and forecast accuracy?
Oh, okay. M4, I didn't catch that, which is kind of ironic because it's the name I gave it. In principle, there's no specific algorithmic logic built into it or capacity built into it for that particular purpose, but I can imagine all sorts of ways in which M4 could be applied for that purpose. But that's not a unique property of M4. In principle, you could actually apply principal components regression or process simulation models to do the same kind of thing to come up with those sorts of estimates.
Okay, thank you. Other questions? I don't see any more in the chat.
Oh, hey, Sean, this is Forrest. Let me ask that question a different way. From the work you've done with M4, do you have a sense, I mean, given that the quality of the model developed by any machine learning approach is going to be determined by the quality of the input variables, do you have a sense already as to where you'd get the most bang for the buck in terms of investments in improving inputs to the M4 system?
Well, I think there's all sorts of broad. Well, thank you for the question, Forrest. That's a great one, and that kind of goes back a little bit to our last slide, and maybe I'll navigate back there. So right now, and I should explain this at the moment. Because we want to do apples to apples comparisons with the existing system. So the only input variables we've considered are of the same type that are used in an existing operational WSF systems. So this is predominantly SNOTEL or other measurements of snowpack. In all cases, though, ground-based measurements, station-based measurements, as well as precipitation and antecedent stream flow. So we did that for the purposes of our hindcast testing and our operational forecast testing to ensure a reasonably apples-to-apples comparison. We just kept with that. That said, I think there are a whole bunch of really powerful directions going forward. Whether it's M4 or not as your prediction platform, that will these alternative predictors can be potentially very, very powerful. There's reason to believe that M4 can capitalize on them more effectively because of the capabilities we've built into it, and therefore is in a way is a better way of testing the value of these alternative predictors, but it's not the only way to do it. And so what are these additional predictors? A bunch of remote sensing or assimilation data, especially around snowpack, but not exclusively. Things like soil moisture, initial conditions, precipitation, various other things are useful. So, existing system of SNODAS, MODIS-derived snow-covered area maps or Landsat-derived maps, things like the ASO, where you have these really detailed SWE maps. WWA and Boulder's been doing some amazing stuff with that as well. So I think that's a pretty clear direction to go in. The largest at this point, given that there is a reasonably good snow monitoring network across the Western U.S. SNOTEL isn't perfect. I think many of us know the limitations of it, but it's a pretty good index of what the overall snow water equivalent is, and we can definitely refine that using these other methods, and that's definitely a right direction to go in. But all of that notwithstanding, really the largest source of prediction uncertainty between the forecast date and the entire target period is future weather, or more specifically, seasonal to subseasonal climate. And how important that is varies. If you're in the Sierra Nevada, it's almost completely snowmelt dominated. But if you're looking in the Southwest, you've got the North American monsoon there. If you're looking in like the Rocky Mountain, like Missouri headwaters, you've got also a lot of summer rainfall there. And also, even with an early season forecast, say you're in January, well, you don't know what the snowpack is going to be. It typically peaks around April-ish, March, April. So knowing that future weather is really important. So one thing I'm really excited about looking into more is the value of seasonal to subseasonal S2S numerical climate models. That said, we're not the only people looking into it, and there have definitely been some challenges with it, but there's also been some progress lately. So I think that's potentially a very productive sort of long-term direction. Does that address your question, Forrest?
Yeah, thank you. Appreciate it.
Yeah, you bet.
Okay, we have another question in the chat. Would M4 make it easier or more difficult to add additional forecasting stations or locations? For example, could it facilitate an ad hoc forecast for a gridded location rather than an existing point location station?
Yeah, there's kind of a two-part answer to that. So the thing is, there is no such thing as gridded streamflow data. It's actually kind of a quirky thing. River hydrology, I mean, a streamflow measurement is spatially, it's a point measurement, but it's also spatially integrated, but it's not spatially distributed, right? Because the watershed is a very distinct, discrete boundary. The watershed, the drainage divide. Plus, you're always measuring it at a point because a river is a certain location in the landscape. So the idea of doing, so if I'm understanding the question correctly, if you're trying to predict a spatially distributed quantity, that's not river prediction. That's something else, perhaps runoff, spatial runoff prediction. In terms of if you're talking about using spatially distributed data, gridded data as inputs, definitely yes, it can do it. And I think we have reason to believe that M4 could capitalize on it a little more effectively than other things. Yeah, so I guess maybe I could get some clarification on that question. I mean, because there is no such thing as gridded river runoff data.
Jeff, did that answer your question, or did you have any follow-up on that? Oh, he says that was helpful. Thank you. Okay.
Okay, you bet. There's actually another part of that question in there, which is sort of the question of how easy it is to apply it. And it is a little more involved than a conventional linear Gaussian model, as you would expect. But again, due to the AutoML features we built into it, it's really not that difficult. In terms of the actual input that a person has to give to the model and the time invested in doing that, It's actually less than conventional methods because it can deal with things like nonlinearity and funky prediction intervals and stuff like that without manual user intervention. So it actually requires less work from a hydrologist to set up an M4 model relative to a conventional statistical model, or at least do a good job of it. The only tricky part, as it were, is that because you are training 6 semi-independent AIs, and the whole process of training AI, especially neural networks, is not necessarily particularly quick. The actual computational time is considerably longer than a conventional linear Gaussian method. Again, though, we've built just the methods we've built and the way we've implemented them, combined with some limited sort of like baby steps in parallel computing, really makes it pretty feasible. It takes, it varies, but somewhere between 10 and 20 minutes for it to train an entire system on a given forecast point. Whereas Viper, which is the software that we use for PCR internally, takes maybe 4 or 5 minutes, something like that, to do all the predictor selection. So it's doable.
All right, thanks. One more question. Can you speak again to the schedule for deployment as the operational system for NRCS?
Yeah, that is a great question. I have that question too. So we're working towards that. So M4 is basically ready to go. It's that platform, that interface, that is the kind of critical gap that needs to be filled. We're working very actively on that in partnership with some folks externally to do kind of build a sort of an R&D level prototype to explore what exactly that would look like, what that interface looks like. And it's actually a really interesting process. The operational hydrologists working together with computer scientists to kind of think through that process of, okay, what do I need out of this system? What do I need to be able to control? What do I need to have automated? All these sorts of things, then build a system like that. But that process is underway, and we expect by the end of the year, we're going to have a functioning prototype. That next step of and then also it's going to be almost certainly a phased implementation into the operational environment. So I'm expecting within the next perhaps a year from now, we may be looking at some increased operational adoption across the unit, and then at some point after that, more comprehensive implementation. The platform or interface we're building for it now is it's kind of an R&D level prototype. We'll have to, if that's successful and we're able to test our ideas, then we'll have to take it to the next step and build an actual production system that will run for years and years and years and be used by the whole team.
Okay, and then one follow-up: what are the plans for model archiving / documentation for forecasts?
Yeah, that's a great question too. That's part of that process of building an interface. I imagine it's going to kind of follow our existing protocols, at least in a general sense. So all the forecasts are archived in a database. And we're going to continue to do that. As for the actual models themselves, so the whole thing's built in R. So these are mostly R object files and a bunch of Excel and text files with essentially metadata that's required to recreate each model. That's how the models the trained models are stored. And we need that in order to run it operationally. So when I mentioned that it takes 10 to 20 minutes to train a model, that's just initially to develop it. Once it's trained, it runs essentially instantaneously, and that's done by grabbing these archive model structures and running it with a new sample with new data operationally. So all of that's going to be it has to be archived because it won't run otherwise. Plus all the forecasts will be archived just as our current forecasts, I believe, are just fully archived in the database. So yeah.
All right. Well, thank you so much, Sean, for a great presentation, and thanks everyone for all the good questions. We will wrap up the webinar for today, but I'll remind you that this recording will be posted on the Western States Water Council webpage, and due to a request here, if the slides will be posted, I'll also look to put a PDF of the slide deck there as well. I did want to mention they're in the process of updating the website, so there might be a short delay in getting that up, but do look for it here in the near future. And thanks again, everyone. Have a great day.
Thank you.